For more than 200 years, mankind has been experimenting with flight, constantly perfecting the skills and the technology to take us higher and faster. In the early days of aviation, problems of high-altitude flying were ignored. In 1875, 3 French aeronauts attempted a high-altitude ascent in a free balloon called the Zenith. Insufficient knowledge of human physiology and the effects of high altitude contributed to a tragic accident. At 26,000 feet, all 3 lost consciousness. Only 1 survived when the balloon touched down. In 1931, a pressurized cabin was tried for the first time in the form of a gondola, which was originally designed to be a stratospheric balloon. In 1939, the first high-altitude passenger-carrying aircraft was developed, the Boeing 307 Stratoliner. Pressurizing an aircraft cabin is a convenient means of controlling some of the hazards of high-altitude flight. Maintaining a comfortable and safe environment for human occupancy involves the simultaneous control of temperature, humidity, air circulation, and cabin pressure. Most pressurized aircraft today cruise at altitudes between 25,000 to 51,000 feet, while keeping the cabin at a comfortable altitude of 6,500 to 8,000 feet. Flying pressurized aircraft has certain advantages. In most cases, an oxygen mask does not need to be worn. The risk of decompression sickness is minimized. There is less noise and vibration during flight. There is better control of temperature and air ventilation, and there are fewer trapped gas problems. What are the basic mechanics of pressurization? Ambient air is introduced into a compressor. Once the air is compressed, it heats up rapidly. The heated air is then sent through a cooling unit and introduced into the cabin. By use of overflow valves, the air comes in quicker than it leaves and creates a high-pressure environment. Various aircraft use different types of pressurization systems. 3 of the most popular systems include isobaric. This is the most common system. The cabin altitude is preset and remains so throughout the flight. Isobaric differential. This type of system is used mainly in military fighter aircraft because the isobaric system is too heavy. Upon ascent, the cabin begins to be pressurized until it reaches a preset altitude. If the ascent is continued, a constant pressure differential is maintained. Sealed cabin. This system is used only in spacecraft that carry their own supply of gases to create the pressurized environment. While there are numerous advantages to having a pressurized flight, there is one major disadvantage. There is always the chance of losing pressurization. There are 3 major types of pressurization loss. Slow decompression, when the cabin loses pressurization during a time interval greater than 10 seconds. It is potentially the most dangerous type of decompression, since you may not be aware that the cabin altitude is going up. Rapid decompression, when there is a total loss of cabin pressurization within 1 to 10 seconds. Explosive decompression, when cabin pressurization is lost in less than 1 second. This rapid change can occur faster than the lungs can decompress. Therefore, it is possible that lung damage can occur. Please note that the main differences among each of these types of decompressions is time. However, there are other factors that contribute to how fast an aircraft will decompress, and they can affect time. These factors include size of the opening in a damaged aircraft. The larger the opening, the faster the decompression. Volume of the cabin. The larger the cabin, the slower the decompression, with all other factors being equal. Pressure differential. The greater the pressure differential, the more severe the decompression. Pressure ratio. When cabin pressurization is lost, aircraft compressors will continue to operate. The rate at which the compressed air comes in dictates how fast pressure is lost. Altitude. The greater the altitude when the decompression occurs, the more severe the physiological effects. Physical characteristics of a rapid decompression can cause the pilot operational problems. For example, noise from a decompression can range from a hissing to a very loud explosive sound. Operationally, there can be a disruption in communication. Fog will form with a decrease in both temperature and pressure associated with decompression. Visual operations may be affected. Pilots have also mistaken fog for smoke in the cockpit. Flying debris will move towards the opening and could cause injury. Pilots and passengers not using their seat belts have been known to involuntarily exit the aircraft. Dust and dirt may cause visual problems. Cooler temperatures will occur as the pressure or air departs the cabin. Frostbite and hypothermia can occur. In addition to the physical effects, there can be physiological effects from a decompression. The middle ear, sinuses, and digestive tract contain gases that will expand with decreasing pressure. Decompression sickness can occur due to the nitrogen in the body coming out of solution and forming bubbles. The colder temperatures at altitude can cause hypothermia, a problem previously mentioned under operational issues. With the rapid decrease in partial pressure of oxygen, there will be an oxygen deficiency in the blood, leading to hypoxia. The emergency could produce an increased rate and depth of breathing, causing hyperventilation. Each of these problems has a separate training module available if you need further explanation. If you experience a decompression, you should use the following procedures. 1. Don your oxygen mask. You should be able to do this in 5 seconds or less. Check to make sure the air is flowing 100% in your mask. 2. Maintain aircraft control. 3. Descend to a lower altitude, preferably 10,000 feet or below. 4. Land the aircraft as soon as possible, and if needed, obtain appropriate medical help from someone who is familiar with aviation physiology. In summary, the basic mechanics of pressurization are: ambient air is introduced into a compressor. The air is compressed, it heats up, and is then cooled. The air is then introduced into the cabin, where overflow valves control the air to create a high-pressure environment. Remember, there are 3 main types of aircraft pressurization systems. Isobaric, where the cabin altitude is preset and remains so throughout the flight. Isobaric differential. This one is mainly used in military aircraft. Upon ascent, the cabin begins to be pressurized until it reaches a preset altitude. If the ascent is continued, a constant pressure differential is maintained. Sealed cabin, used only in spacecraft. The 3 types of decompression are slow decompression, where cabin pressurization is lost in 10 seconds or more. Rapid decompression, where the loss of cabin pressurization happens within 1 to 10 seconds. Explosive decompression. Cabin pressurization is lost in less than 1 second. Factors that affect the time of a decompression are size of the opening, volume of the cabin. Pressure differential. Pressure ratio. Altitude. The kind of physical characteristics you can expect from a rapid decompression are noise, fog, flying debris, cooler temperatures. The physiological effects of a decompression are trapped gas expansion, decompression sickness, hypoxia, hyperventilation, hypothermia. If you experience a decompression, you should 1. Don your oxygen mask, 2. Maintain aircraft control, 3. Descend, 4. Land the aircraft. The bottom line is, know your aircraft. Be sure to pre-flight your oxygen equipment. Tie down any unanchored equipment in the airplane, especially if you are going to pressurize the aircraft. These are just a few preventive steps that you should take to reduce potential problems with a decompression.